Okay, hi everyone. Let's go ahead and get started. Welcome back to MAT1841. So last time we talked about BC dimension and shattering functions. And so we introduced that as well as gave some examples of BC dimensions of particular set systems. So today what we're going to do is we're going to combine BC dimension of multiple set systems, and then we're going to apply BC dimension to trying to understand generalization error. So the way you should think about this intuitively is if you think of a set system as corresponding to some concept class, like maybe the sets that make up some set system correspond to, say like color or like some other class. Maybe you want to combine color with like shape, and that might be some other concept class. And then you'd have two different set systems that you then combine together to get this a new set system for classification. So let's first start and just consider two different classes. So this is Lemma 5.11 in your textbook. So suppose we have two different set systems on the same set. So X and H1 and X and H2 are set systems on the same set X. Then I claim that the shattering function of the intersection of these two set systems for any n is less than or equal to the product of the shattering functions on each of the individual set systems for n by h2 of n, where we're defining this h1 intersect h2 as the set for all h1 intersect h2 as sets inside of these concept classes, where h1 comes from h1 and h2 comes from h2. So you might think of this as like color, and this is like shape, or something like that. And then you're looking at the new concept class that's both color and shape. Let's go ahead and prove this. The proof is fairly straightforward. Let's have some set A contained in X of size n. Well, then clearly, let's also let the set S be equal to A intersect H for all H in H1 intersect H2. Okay, so these sets S are subsets of A that correspond to their intersection. So these are the representations. So we need to count the size of S, basically. So by definition, we know that S is equal to A intersect H1 intersect H2 for all H1 in H1 and H2 in H2. And well, it's pretty easy to show that this is then equal to the intersection of A intersect H1 intersect A intersect H2 for all these same conditions, and H2 in H2. But of course, this then implies that the size of the set, the size of S, is less than or equal to the size of A intersect H1 for H1 in H1 times the size of A intersect H2 for H2 in H2. Okay, which is, and then all I have to do is you choose some maximally shatterable A. H1 intersect H2 of n. Well, then we know that, and these are clearly some other shatterings of A under these two different sets. And so, and even if the A isn't maximally shatterable under H1 or H2, I mean, it's still clearly bounded from above by that. And therefore, pi of H1 intersect H2 of n is always less than or equal to pi of H1 of n times pi of H2 of n. Okay, and this sort of makes sense, right? Because basically what we're saying is that if you have some concept class and you combine together two different concept classes, and then you look at how many pieces you can shatter a set of size n in one concept class versus the other, clearly you can't shatter, using both of those, you can't shatter the sets of that size into more than the product of the two. So that should sort of make sense. And this allows us to basically take the Boolean end of concepts. So you're, instead of using a concept class of color and the concept class of shape, here this is the concept classes of things that are like red squares or blue triangles, things of that sort. Let's see, so this allows boolean and of concepts. And another example, just to give a slightly more mathematical example, if x is equal to r to the d, and h1 is equal to the set of all half spaces. So what we worked on a lot last time. And we know that h2 is also the set of all half spaces. Then h1 intersect h2 is equal to the set of all intersections of two half spaces. Because it's just equal to being in half space 1 and being in half space 2. And we can extend this to Boolean ANDs of many concepts. So clearly we're only doing the case where we have two different set systems, but you can do this for an arbitrarily finite number of different set systems, as well as arbitrary Boolean functions. So it doesn't just have to be AND, you can also have other functions of these Booleans. So for example, if given k different concepts, given k concepts, h1 through hk in H, and a Boolean function f, we're going to define the set. So no, these are concepts, not concept classes. We're going to be working over the same concept class right now. We're instead just creating a new concept based off of multiple examples from a single concept class. So like if you think about the previous, when we were talking about last time, we talked about the VC dimension of intervals on the real line. And then we talked about the VC dimension of two different intervals on the real line. And so this is basically extending it that way. So you're using the same concept class, but you're doing it multiple times. Even though it's the same concept, doing it multiple times allows you to capture more information. We're going to define the set comb for combine of f h1 through hk as equal to the set of x in x, such that f of h1 of x through hk of x is equal to 1, where we're defining this concept as a function, as basically an indicator variable. So we're overloading the notation hi as both the function as an indicator variable and also as the set itself. So hi of x is equal to 1 if and only if x is equal to x is in hi. Okay, so we're overloading things slightly, but you can just think of them as also indicator variables. And well, let's see a couple examples of this. So well, we had the first one where f is the AND function. So we're just taking the AND of a bunch of concepts. Well, in that case, combining all these, h1 through hk, is equal to the set x in x, such that pi of hi of x is, sorry, not pi, let's product. The product of all these, product of the hi of x's is equal to 1. So basically you need it to be in all of these sets. And as another example, f is the majority vote function. Majority vote function, by which we mean that f is true so long as at least half of the other statements are true. So we can write this as combine f of h1 through hk is equal to set x in x, such that I'm going to write this in a sort of weird way, but it's basically just so long as half of one. All that's saying is that so long as if you sum up together all of the HIs, you're in at least half of one. Just a weird way of writing it. There are many different ways you could. So note that we're defining this as a set. But of course, we can also define concept classes out of sets. So we're going to define a new concept class. So define a new concept class. I'm going to use capital com sub f and k of H as the set combining together comma of F H1 through HK such that HI is in H. And this is a new concept class. So for example, if we had combining of the AND function where k is equal to 2, that gives us precisely the concept class that we talked about up here. And so basically the punchline is that by repeatedly asking about these sets in one concept class in this sort of Boolean way, you can create new concept classes that are more discriminative. So maybe just taking intervals in the real line isn't very helpful, but if you take a finitely large number of sets of intervals in the real line and look at all their intersections and unions, well, that gives you a much more powerful concept class, and that you can express more things in. Okay, and we, similar to this lemma above 5.11, we can also say something about the shattering function of these sorts of things. And this is generally true that for any Boolean function, function f and hypothesis class, so this is a new name that we're giving for H. It is still the same H, so it's just some set of sets from an integer k. One of the things you'll notice as we go through lecture today is I'm going to start sprinkling in more and more terms showing how these set systems apply to basically machine learning. And so a hypothesis is something that you might have in machine learning. It's not really something that you have in the set system, but you can think of the set system as a class of hypotheses. So for example, maybe you have some set system that you think corresponds to something like color. But anyway, we want to say something about the shattering function. So pi of this new concept class, comp fk of h of n is less than or equal to pi of h of n to the k. Okay, so that's basically what we had here as this product, except in this case, we have h1 and h2 are the same all the way through hk. And we're just drawing multiple things from that. We're not going to prove this because the proof is basically the same reasoning as in our previous example, same reasoning as 5.11. Okay, just generalize to higher k. And let's go ahead and give a theorem about the VC dimension of these things. So if the VC dimension of H is equal to V, then for any Boolean function, f and integer k, we know that the VC dimension of this combined concept class, fk of h, is equal to O of kv times log of kv. Okay, so we can get also, and this will follow from the shattering function that we've already proven stuff about. And basically, when you combine together concept classes, you get something that has a higher VC dimension. How much higher? Exactly this much higher. So if we let n be equal to VC times this VC dimension, is because it's going to take a lot of time to write that out each time. So we're going to let that be n. We're going to use n because, of course, the VC dimension is going to be the size of the largest set that can be shattered. And so we can, n makes sense right now as just the size of that set. Well, by definition, there exists a set of endpoints shattered by this concept class. And we're going, let's call that set S. And last time we proved Sauer's lemma. So that was the one that had the sort of double induction that we did at the end of class yesterday that I sort of rushed through. But by Sauer's lemma, we know that pi h of n, so the shattering function, is less than or equal to n less than or equal to v, which is, of course, less than or equal to n to the v. So there are, at most n to the v ways of partitioning S using sets in H. But of course, each set in this combined concept class, fk of h, is determined somehow by k sets in H. So these might be ands, these might be ors. There are other, whatever way you're combining these things together using your Boolean function f. So that means at most n to the v to the k, which is n to the vk, ways of partitioning points. Partitioning points using comb of fk of h. But we know that S is shattered. So S is shattered. So that means 2 to the n must be less than or equal to n to the kb. Okay, so this is just by definition. And that implies that we know that n is less than or equal to kb times log 2 of n. And we're going to say that if n is greater than or equal to 16, so if it's less than that, then this doesn't quite hold, but it's, we're only talking about asymptotics, so it doesn't matter. So if n is greater than or equal to 16, then we note that log 2 of n is less than or equal to root n. And when plugging that back in, that implies that kb log 2 of n is less than or equal to kb times root n, which implies that n is less than or equal to kb root n, which implies that n is less than or equal to kb squared. And plugging that back into this, so plugging that back in, what you get is that n is less than or equal to kb log 2 of kb squared, which is equal to 2 kb log 2 of kv. And so that proves the theorem. It's actually slightly stronger than that, but we had to use the asymptotics because for a really small n, it doesn't quite work. Okay, so basically this means that we can combine together concepts, and you can even take the same concept class and combine together multiple concepts, and that's sometimes quite useful. Since in the case of color, for example, like, well, it's hard for something to be both red and green, though that's possible. But for other types of concepts, like maybe one concept in the email classification example, maybe one concept was spam emails and another concept was academic seminar emails, and maybe there is sometimes some overlap between the two of them. And so it is helpful to be able to combine together these concept classes into bigger concept classes like spam and seminar email, or spam or seminar email, or whatever. Okay, now that we've done that, we're going to take some time and prove it's called the Key Theorem in the textbook, and this is going to be a very important theorem. And then we're going to apply this theorem to understanding how this VC dimension relates to the generalization problem when you're training a machine learning system. So this is going to be theorem 5.14. It's going to be called the Key Theorem. And what we're going to do is we're going to just let xh be a set system. And now we're going to introduce something new. We're going to introduce a probability distribution, a probability distribution over x. And we're going to let n be an integer satisfying several conditions, satisfying n is greater than or equal to 8 over epsilon, and n is greater than or equal to 2 over epsilon times log 2 of 2 pi sub h of 2n plus log of 1 over delta. Lots of technical conditions. We'll see how why each of these things is important. So these are the conditions on n, and then we're going to let S1 consist of n points drawn from D, with replacement. Okay, so we have some probability distribution, and we're picking balls out of this bin, this probability distribution D, with replacement. And then our claim is with probability at least 1 minus delta, every set in H of probability mass greater than epsilon intersects S1. Okay, so let's take a step back and think about what we're talking about now. So now, in addition to just having a set system, we have some process of drawing samples from the set system that's well defined. And what we're doing is we're drawing endpoints from the set system, and then we're arguing that with high probability, there's some intersection between all of the high probability mass concepts in H and our set S1. And this is then going to play a role when we start thinking about this as a machine learning model, where you're drawing some endpoints initially for your training data, and then when you see, and then you're going to ask whether or not that intersects with one of your concept classes, and then later you're going to see that when you draw another set of endpoints from your training data, say as your test data, that you're going to get similar results. Like somehow this concept class, if it works for your training data, it's also going to somehow work for your test data to some degree. So that's the basic premise of all this, though it's going to take a little bit of work to prove. So note that we do have this weird condition that n is on both sides. We don't really need to worry about that because on one side there's a logarithm, and so for large n, this is a condition that you can pretty easily satisfy. So there are some technical conditions. I put them in the online version of the notes. I'm not going to go through it too much in detail. But let's go ahead and prove this, and we'll see the consequences of this theorem. Okay, so if we let some event A be equal to the event that there exists some H in H I'm going to use the function mu to mean probability mass. So this is pretty standard if you've taken the probability course. So mu of H is going to be greater than or equal to epsilon, such that H intersect S1 is the empty set. So what do we mean by that? So this is the event that you have some big set in H that it does not intersect your the set that you've drawn of D points. So well, ideally, we're going to show the bound probability of this event. Okay, now the next thing we're going to do is we're now going to draw wait a moment. Did I do that right? Okay, no, that's right. Yeah. So now we're going to draw a second set, S2, of endpoints. From D. Just a moment, let me make sure I have all my notation correct. Okay, yeah, I think I have all my notation correct. Okay, so we're drawing a second set of S2 of another endpoints from D. And let's let the event B be equal to the event that there exists some H in H with H intersect S1, or H not intersecting H1, or S1. So you're drawing some other set of points, but you're drawing them with replacement. So there's some possibility that they intersect, but this event will be that there exists some H such that they don't intersect, but we know that H intersect S2, the size of that intersection is greater than or equal to epsilon over 2 times n. Okay, note that that's an actual size, not a probability mass of the set. So that's the actual cardinality, the number of points. It's going to be greater than or equal to epsilon over 2 times n. So what have we done now? We've drawn endpoints, and we're drawing another set of endpoints, and somehow we're going to use this to bound probabilities for the first set of endpoints. So note that it. Oh, no, that's probability mass. So that's the amount. So H is a subset of X, right? And we have some discrete probability distribution D on all the elements in X, right? And so mu here is you're adding up the probability of picking out something from H. Yeah. So yeah, so it's a probability mass. So like think probability theory. So now if H intersect S1 is the empty set, so that's obviously one of the things we want for the set in B. And the mass of U, the mass of H is greater than or equal to epsilon. So somehow we're looking at some event that's some combination of A and B here. So we're looking at some H that satisfies both A and B simultaneously. So both A and B are events saying there exists at least some H somewhere. So they don't have to be the same H. But we can ask, well, what if it's the same H? And so that's what we're asking here. So if it's the same H, basically, then we know that the expectation of H intersect S2. So what's the size of that? Well, that is the expectation of the sum of a bunch of indicator variables, right? So for every X in S2, you're asking, is that X in H? Right? So this is clearly, the expectation of that size is clearly no software update. The expectation of that size is clearly the expectation of the sum of all these indicator functions. But these are all independent indicator functions, since we're drawing all these points independently from this probability distribution. And for any one point, the chance that you're going to draw it is going to be, well, epsilon, right? Or at least epsilon. So this entire thing is going to be greater than or equal to n epsilon. Right? Because you have an indicator variable, and so the expectation of an indicator variable is just the probability that that's set to 1. But that indicator variable is set to 1 when you draw something from H, and the probability of drawing something from H is at least epsilon. And you're doing this n times, and so the expectation is greater or equal to n epsilon. Also, well, I mean, we have expectations, and if you go back to like all things we did with expectations and variances, one of the things we might want to do is we might want to do a tail bound. So we've done a lot of tail bounds in our time in this class. Let's do another one. So, well, we could try to use Markov, but instead we're going to use Chebyshev for this particular proof. And so in order to use Chebyshev, we also need the second moment, or we need the variance, right? So let's compute the variance of this thing. Well, the variance of H intersect S2, well, we know that the H intersect S2 as a random variable is just the sum of a bunch of indicator variables. And so that means that we know that its variance is n times the variance of all these indicator variables in H. And that's equal to n epsilon times 1 minus epsilon, right? Because the variance of a Bernoulli random variable is just epsilon times 1 minus epsilon. And so this is less than or equal to n epsilon. So now we can apply Chebyshev. So by Chebyshev, we know that the probability that H intersect S2 is greater than or equal to epsilon over n over 2 is going to be less than or equal to n epsilon times 2 over n epsilon squared.
So for variance, why is it equal to like what is it equal to n epsilon?
Because it's n times the variance of each of your of a Bernoulli random variable, right?
Oh yeah, but I mean the probability mass is greater than or equal to epsilon.
Oh yeah. Yes. So let's see. Oh yeah, I think there's something wrong. Yeah, you're right. Like there is like some bound here. But this is going to be less than or equal to. Yeah, no, you're right. Because we have a greater than or equal to, so that messes stuff up. Okay, but anyway, so now we can apply Chebyshev, and so this is then equal to 4 over n epsilon, which is less than or equal to 1/2, because one of our original conditions was that n is greater than or equal to 8 over epsilon. Right, since that was one of our original conditions up here, and that's the reason we made that assumption. You may or may not act like you don't actually. So this is one of those proofs that you can change up the constants a little bit and still get a proof that's basically the same. And so some of these technical conditions we just chose to make proving it easy. But anyway, so now we've done that. This means that the probability of somehow the probability of B given A, so it's greater than or equal to 1/2, right? Because this is because the event that we're looking at right now is that the same H for both event A and event B is satisfied. And so clearly that means that the probability that you have event B given that you have event A is at least 1/2, because like this is a special case of that. Since this only counts when it's the same H for both A and B. And this implies that the probability of B is greater than or equal to 1/2 of the probability of A. Okay, so that should be clear. If B given A has at least 1/2 probability, then the probability of B is at least 1/2 of the probability of A. So thus, to prove that probability of A is less than or equal to delta, it suffices to show that probability of B is less than or equal to delta over 2. Okay, so all we did here is we introduced this new set S2, that's disjoint from the set S1 to, and then now all we have to do is bound this other event probability B, which is going to be slightly easier for us to characterize. Now what we're going to do is we're going to use a trick. So a moment ago, we drew endpoints and then we drew another endpoints, right? And so that was how we sort of defined these probability distributions. Now we're going to use a trick where we're going to instead draw 2 endpoints and then partition them between the two different sets. And clearly these are the same probability distributions, right? So if you start off with draw endpoints and draw another endpoints versus you draw 2 endpoints and then you randomly partition the 2 endpoints that you've drawn into both of the sets, these are the same probability distributions. This is a sort of weird way of doing it. But we'll see why we want this weird way. So now we're going to consider drawing S3 of 2 endpoints and randomly partitioning it. Randomly partition it into lists S1 and S2. So this clearly yields the same probability distribution. Same probability distribution. But somehow we're going to make use of the fact that we're drawing all of our 2 endpoints at once, and then each point has 1/2 probability of being in one side or the other, S1 or S2. And that'll play a really important role. So now we note that, but importantly, we're not going to partition it yet. So somehow we're going to think about this, and then we're going to think about the partitioning process later. So that would yield the same thing, but we're only going to draw the points now, and then we're going to hold off on partitioning. So note that we know that the size of S3 intersect H, given that H is in H, is less than or equal to pi H of 2n. Right, and that's just by definition of the shattering function. So we know this is true because well, whatever size it is, well, I mean, it is the set is of size at most 2n, and so the subsets that can be partitioned using our concept classes is going to be less than or equal to the shattering function because, well, the shattering function is the most that you can do. So we know that the probability of B is going to be less than or equal to the sum over, let's call this H prime in S3 intersect H given H in H, of the probability that S1 intersect H prime is equal to 0. So the size of the intersection is 0, so they don't intersect. And S2 intersect H prime is greater than or equal to epsilon 2 over n. Okay, and this is just by using the event B, since so the event B is well defined, and it's of whatever set of things are in S1. We're going to claim that the things that are in S1 have to be equal to 0 after this partitioning process, which we haven't done yet. So there is some partitioning process, we haven't done it yet. And note that this is then less than or equal to pi H of 2n times, because that's the number of sets, right? So this is the total number of sets, and so that's if that's the maximum possible number of sets in the summation, times this probability of S1 intersect H prime is equal to 0, and S2 intersect H prime is greater than or equal to epsilon over 2n. And this is for all H prime. So to prove probability of B is less than or equal to delta over 2, it would suffice to show that this probability of S1 intersect H prime is equal to 0, and S2 intersect H prime is greater than or equal to epsilon over 2n. Now this thing is less than or equal to 8 over 2 pi H of 2n. Oh, sorry, no, that's not a 8, that's a delta. Okay, so we're just rewriting stuff right now. Note that, of course, the size of H prime is greater than or equal to epsilon over 2n, because otherwise, well, S2 intersect H prime would be less than epsilon over 2n, which is not true. So we know that the size of H prime is at least epsilon over 2n, unless we know that the probability given and here we're going to do our random partitioning. So we haven't partitioned stuff yet, but now we're going to randomly partition. Probability over our random partition of S3 of S1 intersect H prime equals 0. Well, what's this going to be equal to? Well, it turns out this is going to be less than or equal to 1/2 to the epsilon n over 2. Because for each element, we have a 1/2 chance of putting it in one side or the other. And we have epsilon n over, we need to ask, basically, we need to ask what the chances of these things, the intersection is. And so for each of your epsilon n over 2 things, you have a 1/2 chance of like throwing it into, throwing it into the right bin to have an intersection. So because each item in H prime has a 1/2 chance of falling in S1 versus S2. And of course, there's a question of whether or not it like intersects with H prime, but it doesn't matter because we can bound it by the probability that's in S1 to begin with. So, I mean, it does matter, but like not especially. So this is just 2 to the minus epsilon n over 2, which is less than or equal to 2 to the minus log 2 of 2 pi sub h of 2n plus log 2 of delta. Did I set that up correctly? Yes, I did. And when you plug stuff in, this ends up giving you delta over 2 pi h of 2n, which completes the proof. Okay, so this was a sort of weird proof technique that is actually pretty common. It's known as double sampling or as ghost sampling, where you look at this, you're looking at this distribution in 2 different ways, and each way gives you some other fact about the distribution. And in this case, we were postponing our partitioning process until the very end, and let us say something different about what we could have said if we had done the partitioning at the very beginning. Any questions about that? So I mostly gave this proof because it's a sort of cool proof technique where you're looking at the same probability distribution, but twice in 2 different ways. Okay, so now we have this complicated theorem with lots of technical conditions. Well, what does that say about machine learning and the classification problem? It turns out that this is closely related, as I was alluding to earlier, to the classification generalization problem. Classification generalization problem. So let's think about the setup really deeply, or I mean, properly in the context of machine learning and training sets and test sets. Okay, so one of the assumptions that whenever you're doing some sort of statistical classification is that given a probability distribution D over a space X, we receive a training set. So we receive a training set S drawn from D, and we want to predict well on new points from D. Okay, and let's let something called C star be contained in X be a target concept. So for example, spam emails or things like that. And then we have some other target concept. So we want, which we're going to call a hypothesis H, which is also set in X, such that, and what we want is that the symmetric difference H difference C star is minimized. Sorry. Too much talking today. I'm given another seminar earlier. But yeah, so C star might be the true set of spam emails, and H might be whatever your classifier is classifying as a spam email. And so we want the symmetric difference. So we want the set of spam emails and the set of what we think to be spam emails to be the same. Oh, so what we're going to do is we're going to define error. So the true error of H is the error on the distribution distribution of the probability mass of H symmetric difference C star. So on everything, like what are all the things that are misclassified? What are all the things that are misclassified one way or another? And I am losing my voice. So luckily I only have another 8 minutes left. Hopefully my voice will hold out until then. So that's the true error. But of course, we also have a training error of H, which is error sub S of H, which is equal to the size of the training set. Okay, so it's the number of things on your training set that you're getting wrong. And somehow we can't minimize error sub D because that involves the entire distribution. What we can do, and what we do is we minimize error sub S, right? We minimize the training error, but sometimes this doesn't minimize the distribution error. You might have heard of something called overfitting, where you get really good on, you get some concept that's really precisely targeted at your training set, but somehow it doesn't generalize to the concept that you actually care about in your full distribution. And so if your set of possible hypotheses were, if like your set script H was all possible subsets of X, then that'd actually be really bad. Because then when you're training, you might just memorize the exact set in your training set. And so in many cases, you actually don't want really high expressive capacity. If you have too much capacity, then you can just memorize the answer, and then you don't generalize very well. And so somehow you want to restrict the set of hypotheses. And so this is why it's important that the set systems have a restricted number of subsets and not just all possible subsets, because otherwise you won't, like, yes, you'd get perfect training error, but like it wouldn't be very helpful. So we turn to a restricted class of hypothesis, a restricted class of hypotheses, these H, which is contained in the set of subsets. So this gives us a set system, X and H. And so the question is, when can we generalize but not overfit? And one answer to that is if the sample size is large compared to the VC dimension. So we're going to let H prime be equal to the set of the symmetric differences instead. And this is going to be the collection of error regions. Collection of error regions. Regions of hypotheses in H. Okay, and we're not going to prove this, but one lemma is that H and HC, H and H prime have the same VC dimension. VC dimension and Shattering function. This is an exercise for the reader. It's also in the previous version of my class notes and on this one. And we're not actually going to prove any more theorems today. We're just going to state some results that are all things you can prove basically using either 5.14 or using the techniques that you used for the key theorem. But so the theorem, this is 5.15. So this is the sample bound theorem. This states that for any class H and distribution D, if a training sample of size, training sample S of size n is drawn from D, where n is greater than or equal to 2 over epsilon times log of 2 times the shatter function of 2n plus log of 1 over delta. We should recognize this from the theorem we just proved. Then with probability 1 minus delta, every h in h with training error sub s of h equal to 0 has actual error, true error, less than epsilon. Okay, so if you can bound the expressive, if you have a low expressive capacity thing, then if you were to get a perfect training error, then it would be relatively close to your actual error. And this, it's actually somewhat stronger than this. And so you can say things about like how much the difference between the two errors ought to be, but that requires a little bit more work, so we're not going to do it here. And the proof of this is just basically applying theorem 5.14 to this h prime. And there are a couple other useful theorems. So this is going to be theorem 5.16, which is the growth function, function uniform convergence. And so if the training sample S is even bigger, sample S has size n at least 8 over epsilon squared times log of 2 pi sub h of 2n plus log of 1 over delta. Then with probability 1 minus delta, every single h in h will have error sub s, the difference between the two errors minus error sub d is less than or equal to epsilon. So basically, if your training sample is big enough compared to the expressive capacity of your model, then the training error is pretty close to your actual error in basically every case. And the proof is similar to 5.14 and 5.15, but you need to apply some turnoff bounds instead. And that's where you get this extra like 1 over epsilon term from.
So is the technical condition supposed to say that my set H has like low express?
So the technical condition is basically saying that if your training set is much bigger than the shatter function value. And so let's actually write this out in terms of VC dimension. So I'm going to write this, this is corollary 5.17. So this is from 5.15. So this one up here, not the other one, but there's a comparable corollary for this one, which is for any class H distribution D and training sample S with size O of 1/2 times the VC dimension of H times log of 1 over epsilon plus log of 1 over delta. If you have training sample that big, that is a training sample with that size is sufficient to ensure that with probability 1 minus delta, every H in H with error of sub S of H equal to 0 has error sub D of H is equal to 0. So basically, what we're saying is that if the training sample is bigger than this function of your VC dimension, then the training error and the sample error are close. And exactly how big depends on exactly which technical conditions you're using and how strong of a statement you're trying to make, of course. But the basic idea, if you think about this in terms of a neural network or some other machine learning model, basically, if you don't have too many, the VC dimension of a machine learning model increases as you have more neurons, right? And so if you don't have very many neurons, if your network is very small, then you don't run the risk of having this generalization error as much, because your training error will be close to your test error. But of course, if you have a super big neural network that can just memorize everything, well, then you run the risk that you're just going to memorize all the training examples and not actually learn to generalize these concepts. And of course, this is only one of the various measures of complexity of a set system. So this allows proving some generalizations. in practice, if you're actually just a deep learner working on neural nets, you're probably not going to worry about this. What you're going to do is you're going to test a bunch of different neural network architectures in different sizes, and then you're going to see empirically if you have this generalization problem. But these sorts of results give you some hope that you can actually, that there is some mathematical justification for why you can do this sort of generalization, and you can make useful predictions even from a relatively small sample of the original data, so long as your model it doesn't have too many parameters, basically. And if you're interested in this kind of stuff, there are also other measures of the expressive capacity of like a network or of a model in general. And so there are things like Rademacher complexity, Shannon entropy. So there are a bunch of other measures for this. VC dimension is only one of them. That happens to be relatively easy to characterize, as we've seen in the last couple of days. So with that, this is the closest we're going to get to actually doing machine learning in this class, which wasn't all that close, but you can sort of see where it connects. And there will not be class next week because it will be reading week, and I will be catching up on grading all of your homeworks. And then we'll start up again the week after on Wednesday. So thank you very much. Any questions? Class is dismissed.